Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this video, we're going to be discussing partial pressure and how to calculate them. Let's get started. Now, if you recall from previous videos in this chapter, we discussed how gases are homogeneous mixtures. They're made up of multiple components, but are a well-blended solution. So if we think about even like the air composition that we breathe, air has oxygen, has nitrogen, has carbon dioxide in it, but we can't individually pick out those pieces. And so when we are studying them and actually doing some measurements associated, we have to think about the fact that they are all contributing to the overall pressure that we're observing. Now, if we think about the air in a room, right? So if you think about the room that you're sitting in right now, there's air molecules that are flying around and there's different components that are making up that air, but there are a couple things that are constant for that entire mixture. Well, one is that the volume that they're all experiencing is the same because they're all in the same room or same container. The temperature that they're all experiencing is also the same because, again, they're in the same environment. But what would be affected is the pressure that they're able to generate, right? So if you look at like the pie graph that's here, we see there's a lot more nitrogen in this mixture than anything else. And so there's a lot more nitrogen molecules bouncing around. And so they would have some amount of pressure that they themselves are able to generate. Our oxygen, fewer amount, but they would also be able to generate some pressure. Our argon and carbon dioxide, same thing. Now, overall, if we looked at all those individual components, that sum would represent the overall pressure of what's in this environment. And so when we are thinking about certain applications, the mixture can be thought of as one gas. And so even though air is a mixture, we can measure the pressure, the volume, and temperature of air as if it were a pure substance. And we can calculate the total moles of molecules in an air sample, knowing the pressure, the volume, and temperature, even though they're different molecules, bearing in mind that those smaller portions, those smaller components, are going to contribute to the overall pressure that we're seeing. So one thing that we can do if we wanted to measure the pressure of a single gas within the mixture is to determine what's called the partial pressure. Now, we can calculate the partial pressure of a gas if we know what portion or what fraction of the mixture it composes and the total pressure. Or if we know the number of moles of the gas in a container of a known volume and the temperature. Now, when we add all those individual pressures up together, that sum will be equal to the total pressure of that solution. And this idea is known as Dalton's law of partial pressures. And again, because each of the gases are really going to behave independently as they are moving around and creating that pressure force. And so the partial pressure of each gas can be calculated using the ideal gas law. And so we've seen this equation before, our PV equals nRT equation. Right? So let's just write that down. But when we were looking at it before, we were assuming that we had this one thing, this homogeneous thing, and we were plugging in a total mole amount to get a total pressure. Well, now if we're looking to find the partial pressure of something, we would simply put the mole amount for that independent piece into that equation in order to figure out its partial pressure. And then the temperature and the volume in both cases, in both of these calculations, would end up being the same because, again, they're in that same environment. And so if we wanted to get the total pressure, we could add those two together. The individual pressures could add up to get us our total pressure. Or we could simply input the total number of moles that's present in this mixture. So let's take a look at a problem. It says you have a mixture of gases that contains helium, neon, and argon. And we want to determine the mass of argon in the mixture. And so a bit of information that we know that's given to us is that the pressure of helium is 341 millimeters of mercury. The pressure of neon is 112 millimeters of mercury. And then the total pressure is equal to 662 millimeters of mercury. And we're also told the volume and the temperature of the mixture. And so if we want to find the mass of argon, we have to think about, well, what can we use? What kind of conceptual plan can we draw off of to help us out? And so knowing that we have the total pressure, as well as the individual pressures of two of the three, we could get the pressure of our argon pretty easily. So if we took our total pressure, and if we subtract the pressure of helium and neon, that would tell us what the pressure of argon would be, because again, the sum of the individual pieces would add up to the total. And so plugging in, we would have 662 millimeters of mercury minus the pressure for helium, which is 341 millimeters of mercury, minus the pressure for neon, which is 112 millimeters of mercury. So when we do that, we take our 662 minus 341 minus 112, and that gets us 209 as the millimeters of mercury of argon, the pressure. And so what we want to figure out is the mass of argon. Well, we've learned before, if we ultimately want to figure out the mass, if we could somehow figure out how many moles are present first, then that would allow us to get to our mass. And so now we have a pressure for argon that we've just calculated, and we also know the volume and the temperature that was previously stated in the problem. And so before we can plug in, we would want to convert our pressure to atmospheres because we need it to be in those appropriate units. So 209 millimeters of mercury, and we would take the 760 from that conversion table I showed in the first video from this chapter, and 1 atmosphere. So now we have 209 divided by 760, and that gives us 0.275 atmospheres. So now if we want to get the moles first, we could take the PV equals nRT equation and rearrange and solve for moles. So moles would equal PV divided by RT. And so my pressure, I'm now going to plug in the 0.275. My volume, I would plug in 1 liter. My R is 0.08206 liters times atmospheres divided by moles times Kelvin. And our temperature would be 298 Kelvin. So now if we plug in, we have 0.275 times 1 divided by 0.08206 divided by 298, and that gets us 0.0112 moles of argon. And then the last step would be to, using our molar mass, get me out of the way here. Using our molar mass, we can then convert from moles to grams. And if we look at our periodic tables, let me just grab mine real quick. That would be, for argon, would be 39.948 is to 1 mole. So then we plug that in. And we end up with 0.449 grams as our final answer. Okay, so a lot of this is really just based on being able to identify what relationships are present and how we can convert from the things that we know to what we're ultimately trying to solve for. Okay. All right, the next problem that we'll try, and I'm going to move me up out of the way one more time. All right. So it says, find the partial pressure of neon in a mixture with a total pressure of 3.9 atmospheres, a volume of 8.7 liters, and a temperature of 598 Kelvin, and the mole amount of xenon is present. So again, a lot of information that we're given here. So we know the total pressure, the volume, the temperature, and the mole amount of xenon. We ultimately want the partial pressure of neon, which means we probably need to figure out how many moles of neon are present. And if we can figure out how many moles of neon are present, then that would allow us to get that pressure, okay? And so first things first, we gotta figure out how much pressure of, what the partial pressure of xenon would be, given the information that we have. And then from there, we would be able to subtract that from the total pressure to get our partial pressure of neon. So we would again use our PV equals nRT equation. And with that, we know that if we have PV equals nRT, the pressure for just xenon would be equal to putting xenon's moles in there. So we would say the pressure of xenon, the partial pressure of xenon, is equal to the moles of xenon times R times T divided by V. And so your mole amount is given to us as 0.17 moles. The R is that constant, 0.08206 liters times atmospheres divided by moles times Kelvin. And our temperature would be 598 Kelvin. And we're going to divide it by our volume of 8.7 liters. So if we take 0.17 times 0.08206 times 598 and divided by 8.7, that would give us a total of 0.95 or 0.96, if we put the proper safe figs, of our xenon, and that's in atmospheres. And so now if we wanted to figure out the partial pressure of neon, well, it's only these two things here. So we could take our total pressure minus the pressure for xenon, and that'll give us the pressure for neon, because again, the sum of those two things will add up to the total. So if we take our total pressure, which is 3.9 atmospheres, and we subtract the pressure of xenon, 0.96 atmospheres, what we end up with is 3.9 minus 0.96, and that gets us a total of 2.9 atmospheres with proper sig figs for your neon. Again, we're exploiting relationships that are present here. Now, we can go a step further and also implement this idea known as mole fraction. So the mole fraction is exactly what the word implies. It's the fraction of the moles. So if we compare the fraction of the total pressure to that of the partial pressures, it would be equal to the fraction between the moles, the individual moles and the total moles. And so this portion here, this relationship of individual moles to total moles, is what we call the mole fraction. And so the mole fraction gets the symbol here, and that's just equal to the individual moles divided by the total moles. Now, if we add up the mole fractions for each of the different components, they should add up to 1, because we're not multiplying by 100. And again, it's the individuals contributing compared to the total. And so what this gives us is a secondary way for us to determine the either the partial pressure or the total pressure, if we have information to allow us to find the mole fraction. So let's try that problem here. So here it says, find the mole fractions and partial pressures in a 12.5 liter tank with 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin, okay? So we have a lot of information here again. So we know the mass of our gases. We also have the volume and the temperature. And so what we want to find is the mole fraction of each of the gases, the pressures of each of the gases, and that total pressure. And so there's obviously, this is a math class, there's always multiple ways that you can do it. But let's tackle doing the mole fraction first. Well, we know if we want to do the mole fraction, we would first want to get both of these gram amounts to moles, because that is how we go about doing that conversion from grams to moles. So this is of helium. We know that's 1. So that would give us 24.2 divided by 4.02 gives us 6.05 moles of helium. And we would do the same thing for oxygen. So 4.32 grams of oxygen, and make sure that we put 32 on the bottom for oxygen because it's a diatomic molecule. So 1 mole of oxygen. And now we take 4.32 divided by 32, and that's going to give us 0.135 moles of oxygen. So if we wanted to get the mole fraction, well, the mole fraction of helium would be the individual moles divided by the total moles. So 6.05 plus 0.135, and that gets us 6.19 moles as your total. Okay. And so your mole fraction is unitless because the moles are being divided. And so this gives us 0.977 as the mole fraction for helium. We also can figure out the mole fraction of oxygen two ways. One way, we can just simply subtract from 1 and get our answer. But if you weren't sure if that would work, you would just plug in oxygen's moles up top, divided by the total moles again on the bottom. And let's calculate that. So that's 0.135 divided by 6.19. And that gives us 0.0218 as our mole amount. And so now with those mole fractions, if we wanted to figure out the partial pressures, there's really two ways we can go about doing this. One way is to simply plug in your moles from above here into PV equals nRT twice, and then that could get you your partial pressures of both of these substances. Perfectly fine to do that. But I do want to show you all how you would go about solving this using their mole fraction. So what we would do is we would solve for the total pressure, so P total, by using our PV equals nRT equation, but we're going to plug in our total moles here and solve for our P. So PV equals nRT, so we would divide this by the volume to figure out that total pressure. So our total moles, which we see above, is 6.19 moles. And then we're going to multiply by the gas constant, liters, atmospheres, moles, Kelvin. And then our temperature, which is 298 Kelvin. And divide all of that by our volume of 12.5 liters. So if we take 6.19 times 0.08206 times 298 and divide it by 12.5, what we end up with is 12.1 as our answer in atmospheres. And so if we want to get the partial pressure using the mole fraction, we could now say that, well, we had that previous formula that the partial pressure for xenon, or for, excuse me, helium, thinking about the last problem, for helium would be equal to its mole fraction, so mole fraction times the total. And so when we plug in the mole fraction, we have 0.977 times the total pressure of 12.1. We plug that in and we end up with 0.977 times 12.1, and that will give us 11.8 atmospheres for helium. Now, to solve for oxygen, we could simply just subtract our 11.8 from 12.1 to get our answer, or we could repeat the exact same thing, but input oxygen's mole fraction. So that was that 0.0218 and multiply that by the 12.1 total. Okay, and so if we do that, 0.0218 times 12.1, we end up with 264 atmospheres. Okay. I hope this video helped you understand partial pressure, Dalton's law of partial pressure, and mole fractions, and how you can do multiple calculations associated with these concepts. Make sure you guys like, comment, and subscribe, and let me know what other content you would like to see. I'll see you guys in future videos. Have a great day. Bye-bye.